Okay, let's continue with that. Let's go for another types of rivet connection that what typically it's going to be concerned a lot with our mechanical engineering design, things like that. Typically, this is the type of the mechanical engineering design with the beam connectors, things like that. We have a pole like that, and then we have a beam, and then we have a Lewis connector just fixed up together like that. Okay, and then we have a load applied to that. So therefore, if we have a load on that, we shift the load applied to that. This is the reaction force. We have V there, and we have a moment there. So therefore, we have V there. We're gonna have a direct shear. So if A prime, if B prime, if D prime, and if C prime respectively, and then we have a moment due to the uh, direct shears up there, and then we have a moment due to the bending moment due to the torque there. We're gonna have an F A double prime, F B double prime, F D double prime, F C double prime respectively. We have a secondary shears there. So therefore, this is the shear there. We have two shears there. So therefore, we gonna sum up with the force on the vector, things like that. We have a total shear force acting on the rivet there. So therefore, we gotta determine all the things together. Okay, we have a primary shear that what I mentioned about that is gonna be F A prime, F B prime, F C prime, F D prime, and then we're gonna have F and double prime respectively. Okay, and then therefore we're gonna add up the vector by the vector addition method, things like that. Okay, let's see the example. Okay, it's set in here. Okay, the figure is gonna show you up there. We have two plates there. Okay, we have a C beam, and then we have a plate there fixed up together by the rivet. Look like that. Okay, this is the 3Ds. Okay, and this is the force acting to that. So therefore, we just move the force to be at the O point there. Okay, so therefore the force going to be up there, and then the moment is going to be there. So the force going to apply to the O point. So therefore, the force there is going to direct the primary shear is going to happen for the direct shears of the force of F sub A, F sub B, F sub A prime, F sub B prime, and F sub C prime, and F sub B prime respectively. And then incidentally, since we just moved the force of F, right, we're gonna have a moment. Okay, so the moment here is gonna be the F sub A double prime, right? And F sub B double prime, and S sub C double prime, and S sub D double prime respectively. So therefore, we're gonna have a rectangle. This is the problem set. Okay, the rectangular steel plate and a C-shaped steel are fastened to each other by four rivets as shown below. Given that AB equal to CD is 120, BC equal to DA is 150, F is 16 kilonewton. All rivets are made of steel having sigma Y of 137.2, and then the safety factor of N is equal to 3 to mean the rivet diameter and the bending stress at each rivet respectively. Okay, so that's what we can do on that. So therefore we find the primary shear since we have the force of 16, right? So therefore we're gonna have a 16 by 4, we're gonna have 4 kilonewton respectively. So therefore, we have a secondary shear. We find the trigonometry. We find the R sub A, R sub B, R sub C, and R sub D respectively. And then we have a formulation on the above equation that what we have got here. We got the R sub A, we got the F sub A, F sub B double prime, F sub C, F sub D respectively, and then we got it equal to 17.7. And then based on the free body diagram on the vector addition of the cosine lower is equal to the magnitude of the total force at A equal to B. So have a look at it, A and B equal to each other, right? So therefore, and B, A and B equal to each other, and B and D equal to each other, C and D equal to each other, right? So therefore, we gonna have we're gonna have RA and RC, RA and RB equal to each other. So therefore, we find the cos theta by the trigonometry. We have RA equal to RB 20 point something, and RC equal to RD is 14, right? So therefore, it's reviewed that the shear force of RA will be maximum, found U to be maximum, and then we found the I equal to RB is maximum. So therefore, since the rivet is made of steel, sigma y is 137, and then since this is the single stress, therefore the tau sub y is 0.6, and then therefore I find the tau sub y is 190 point something. I find the tau design is 64.4 something, and then allowable force, okay, I find 64 3.4, and then I find the rivet diameter is of 20 point something, and then I find the sigma c is equal to alpha b over the projected area. I got the answer, okay, and then I find the bearing stress there is equal to 102.24. That's the answer, okay, and then the combined stress in the rivet connections, okay, that's what I showed, can be able to show you there. See, this one I trying to make it sophisticated. Anyway, I trying to show you the bracket. We have three rivet fix up, some kind of like a bracket, look like that. And then I apply the force on it. And then we have a upper row, we have two rivet, and the down under we have only one rivet. And then I have an eccentric F force just at the B point there. Okay, so therefore this one very sophisticated. I just find the vertical load of 24 kilonewtons, right, applied to the identical rivets in figure 7.11. And then I have a rivet steel. I have a sigma y of 137.2 and a safety factor of 3. I just used the maximum shear stress failure theory to design on it. I trying to find the tensile force in the rivet. Okay, I just find this kind of thing. Okay, you may figure out we have two row, right? Upper row and down under we have the second row, row A and BC up there, right? So therefore, I just use a delta 1 and delta 2 respectively, and then I use a similar triangle there. I find delta 1 or delta 2 is F1 or F2, and then the similarity I find delta 1 over delta 2 is 400 or over 100. I find the relationship of F1 equal to 4F2, okay, and take the moment at point O. You may figure out there. The point O is there, right? Okay, the point O is there. So therefore, I got it there. The point O is there, so I take the moment there is 500 times 24, 100 times F2, 400 times F1, 400 times F1, because that's why we have two rivet on the first row there, right? So therefore, we just simplify everything. I find the result of F1, F2 respectively. So therefore, I make conclusions since both rivet at the B and C are subject to greater tensile force compared to the rivet at A. Therefore, the design should be done at the rivet, right? Because that's why, see, we just to find the greater, right? The greater force acting on the rivet. So therefore, we got to design at the lower rivet. Okay, so the sigma is F1 over things like that. Okay. This is the tensile force, right? And then determine the shear force on the rivet. Then. Primary force FA or FA prime, FB prime, FC prime, 24 over 3, okay, or it's going to be 8. It takes the secondary shear force, take moment around the centroid. Have a look at the figure there, okay, the centroid point there. So you may figure out, because that's why we have 3 right there. So therefore, see the triangle there. So that's why it's gonna be some kind of like a triangle, because the centroid there is gonna away from the base. It's gonna be 1/3 and 2/3 respectively. It's gonna be 1/3 is 100, 2/3 is 200, right? So therefore, we're gonna have, okay, this kind is gonna be 150 times 24, 180 times Q, and 180 times Q, and 200 times 200 over 180 times Q. So divided by the Q based on the figure there. We supposed to be the Q term there, okay? The Q term and Q term, and then this one is a portion of 200 over 180 because why it's away from the centroid, right? Because why this is the away from the centroid 180, away from the centroid 180, it's away from the centroid is a portion of 200. Okay, so therefore this trigonometry is anyway. So therefore we just simplify by the Q term, okay, equal to this. And then based on the free body diagram that what we've got there, vector addition, right? So that's why we find the B term there, okay? Based on the cosine law, VB is going to give maximum there. So the VB term is going to be maximum, going to be 13 point something. So therefore, the design should be done at B then for the design, okay? How's up B there? So determine the combined stress on the rivet. Okay, based on step A and B, design should be done at the rivet B respectively. Okay, so you better figure out there. So okay, let me review that. This is gonna be at rivet A. Okay, this one is gonna be at rivet B. Okay, so okay, we gonna have the maximum shear stress theory. Okay, uh, we gonna have to be done everything's there. Gonna be right there at the design. Put everything there at the equation of the maximum shear stress failure theory. Okay, that's the answer. Okay, that's what we've got there. Okay, and then that's just it. Okay, for the lecture, and then we have some problem set. That what we got to go for it, and then we have number one. Okay, you may go by yourself, and number two is going to be example. It's going to be look like in this example that what I show you for the design, like that. And then this is going to boiler design number three, and then number four is going to be design on the rivet again. Number five is going to be rivet design again. Number five rivet design, and then number seven, 6, 7 is design, the red design, boiler design, and then number 8 is going to be our mechanical engineering design, and then number 9, okay, is going to be our design. Numbers 10, 11, okay, and 12. Okay, very good. One example there. I liked it. Okay. So, okay, you may go for yourself by yourself, okay, for practice, for the problem set. Okay, this is gonna be it for my lecture for today anyway. Okay, that's just it for today. Thank you.